All right, from the relatively advanced differentiation rules that we have most recently covered, we've done the product rule, we've done the quotient rule. Now we've got one last one before some exercises. It's called the chain rule. It's my favorite rule of all, and we're going to make use of it a ton in these live lessons, including for gradient descent. The chain rule has many applications within machine learning. It's critical, for example, for the backpropagation algorithm that's used to train neural networks, including deep neural networks, which are also known as deep learning networks. And more generally, we use it for the gradient descent algorithm, as I just mentioned moments ago. And this algorithm is found in tons and tons and tons of machine learning algorithms. It's must be the most common of all. We're going to talk about it a ton, not only in these live lessons, but throughout my Machine Learning Foundation series. The chain rule is based on the concept of nested functions, which is also known as composite functions. Let's look at an example. Let's say that y is equal to 5x plus 25 cubed, so that whole thing cubed. We can split this up into two nested functions. So we can let the inner part, 5x plus 25, be equal to some variable, say u. And in that case, then y is equal to u cubed. It should be clear now that y is a function of u. Clearly, y is equal to u cubed. And recall that u is itself a function of x, because u is equal to 5x plus 25. This function here, y being a function of x, is nested within this outer function where y is a function of u. And that's it. That's all there is to it with nested functions. Now, how do we apply the chain rule to these? Well, it's an easy way to find the derivative of a nested function. More specifically, if we're trying to calculate dy given dx, but we can break up the equation into nested functions like I have here, then you can consider dy dx to be equal to the product of dy du times du dx. And the du terms will cancel out, leaving us with dy dx, the original derivative that we're trying to compute. So this can make life easier in a lot of situations because it means that we have simpler derivatives that we need to calculate, because calculating dy du and du dx separately is much easier than trying to do them together as one single function. Let's do an example with numbers. So let's say that y is equal to this expression here, 2x squared plus 8, all of that squared. Just as on the previous slide, we can now break up this equation into two separate parts. So first of all, we can consider this inner nested part here, 2x squared plus 8, to be equal to, say, u. And then calculating du dx is really straightforward. 8 is a constant, so that becomes 0. And 2x squared, according to the power rule and the constant product rule, becomes 4x. All right, so easy enough to calculate du dx. And then separately, we can see now that y is equal to u squared. So if u is this part here, then y is equal to u squared. Calculating the derivative of y equals u squared, dy du, is really easy. U squared simply becomes tu according to the power rule. Now that we have tu, we can substitute 2x squared plus 8 back in for u here and multiply things out. 2 times 2x squared is 4x squared, and 2 times 8 is 16. So we've calculated our two separate derivatives, dy du and du dx, for the different components of the nested function. Now we can finally make use of the chain rule from the preceding slide to calculate the overall derivative dy dx. So recalling from the previous slide that dy dx is equal to dy du times du dx, we can simply now substitute in for these two separate parts of the expression. So dy du is equal to 4x squared plus 16, du dx is equal to 4x, and we can multiply that 4x through these two parts, so 4x times 4x squared is 16x cubed, and 4x times 16 is 64x. So here is our final derivative.